Hey everyone, so good to see you guys back here, and I'm hoping that you all are doing great. Excellent, guys. This is Sagar, the your chemistry teacher, and I welcome you to this batch of excellence where we are learning course of organic chemistry. You all are aware that with respect to your boards, JEE as well as NEET. So guys, so far in this course, we have studied one very important chapter, that is haloalkanes and haloarenes, in which we also included reaction mechanism, right everyone? And you all are aware that in the previous class, we also started with another important chapter, that is alcohol, phenols and ethers. So what we did over there, we got introduced to the alcohol, ethers and phenols. We studied their general classification. We studied a bit of nomenclature as well, and straight away we started methods of preparation of alcohol as our first subtopic. And three very important methods of preparation we studied in detail with respect to their mechanisms, which was preparation of alcohol from alkene by acid catalyzed hydration. Second one was by oxymercuration demercuration, and the third one was hydroboration oxidation. Well guys, I'm sure that you all have revised those reactions, solved ample of question on that, and now you all are set to learn our today's class, which is lecture number 2. So let me brief you what exactly are we going to learn in this today's class. Well, so today we'll be continuing methods of preparation of alcohols. So the next method will be where we'll be preparing diol, rather vicinal diol, by a process called as syn dihydroxylation of an alkene. We use two common reagents for this reaction to happen. The first one is osmium tetroxide, followed by action of sodium sulfite or sodium bisulfite in water. However, you see more commonly the reaction is mentioned with another syn dihydroxylation, that is cold dilute caminophore. Yes, everyone, the reaction we also refer it as Bayer's test. That's this reaction. Next, we'll also be learning preparation of diol, but this time it is by anti-addition, and the reaction is nothing but we'll be converting alkene first into epoxide by the action of peroxy acid on alkene. The process will be then referred as epoxidation. Once you get epoxide, then we'll be further carrying out acid hydrolysis to results in the formation of diol. But this time you will see the mechanism is going to be little different. This time it's going to be anti-addition. And then we'll be learning yet another important reaction, but we won't be spending much time on that because we have already spent enough of time on this in the reaction mechanism chapter, that is by the action of aqueous KOH on alkyl halide. Well, after that we'll be learning one more, that is preparation of alcohol by the reduction of ketones. So you will see there will be two reactions by which we can reduce ketone to get an alcohol, either by catalytic hydrogenation or second by using metal hydride. So two new reagents will be getting introduced, that is lithium aluminium hydride LAH and sodium borohydride SBH. Guys, once this is done, we'll be done with methods of preparation of alcohol. So straight away we'll be talking about some physical properties of alcohols. So when it comes to physical properties of alcohol, we discuss about boiling points of alcohol and then solubility of alcohol in water. So this is what we are looking forward to learn in our today's class. So everyone, let's get started with the first method of preparation, that is preparation of, you can see here, vicinal diol or glycol by the action of cold dilute alkaline caminophore. You can also refer this process as syn dihydroxylation followed by Bayer's test. Well, just to see reaction, first understand the way we have represented this reaction. Okay guys, just hold on. Alright, so you can see we have got alkene as our substrate. There it is, alkene as our substrate, which we treated with cold dilute caminophore. It is very important that you mention cold dilute caminophore, because the moment you will say hot alkaline caminophore, it will become a drastic condition, and such conditions where caminophore, alkaline caminophore used at a higher temperature, this reaction results in the breaking of carbon-carbon double bond. So in that case, your product is going to be totally different. Hence, it is essential for us to mention that the reaction is in presence of cold dilute alkaline KMnO4. So just to understand, you can see we have got alkene over here. We know the fact that since it is KMnO4 and we know the fact KMnO4 is oxidizing agent, I'll mention here, it is an oxidant. And this reaction is going to carry out oxidation of carbon-carbon double bond. Being oxidizing agent, I'm just representing symbolically as nascent oxygen. That indicates we are carrying out oxidation. And since I mentioned dilute, so you can see water is mentioned here. Now, for the sake of understanding how you guys can remember this reaction is, if I have got H2O with nascent oxygen, if you add one more oxygen to this water, it's going to be H2O2. Let us assume like that. So if that is our H2O2, ideally you're not going to get formation of H2O2, but for the sake of understanding, imagine if you take that here and break this oxygen-oxygen bond along with carbon-carbon bond, keeping single bond intact, and two new bond if you make between carbon and oxygen, you will say alcoholic OH will be connected to the adjacent carbon, resulting in the formation of ethane 1,2-diol, that is ethylene glycol. Guys, this is just a way of remembering the reaction. We are going to see the mechanism as well. Yes, so what we learned here, an alkene upon reaction with cold dilute KMnO4, which is an oxidizing agent, will oxidize the olefinic double bond, that is carbon-carbon double bond, converting that into vicinal diol, that is a glycol. Well guys, I would like to make it very clear, and I want you all to remember is that this addition of cold dilute KMnO4 is a syn addition. This is a very important feature of the reaction. So imagine if you're going to get some compound where stereochemistry of the product is mentioned, then we just have to ensure that the two OHs which are mentioned in the final product are on the same side or the same side of the plane, because this reaction is syn dihydroxylation. Let us try and understand the mechanism. How exactly does this reaction takes place? Okay guys, see now what we are doing here is let's assume we have got an alkene. So there is carbon-carbon double bond, and this will be attacked by a reagent that is cold dilute KMnO4. Okay, now look. Manganese is a transition metal and they have enough of vacant d orbitals. So let's say pi bond delocalize into the orbital, making oxygen deficient. As soon as oxygen becomes deficient, a pi bond breaks towards one of the carbon, making it rich. That rich carbon attacks at oxygen, making the other carbon deficient. But before it gets converted to carbocation and it could be trapped in the solution, what happens is this lone pair of oxygen atom, other oxygen, attacks at this carbon. So all these arrows that we have shown here are taking place simultaneously. I repeat, a pi bond breaks towards manganese, making oxygen deficient. Alkene being pi bonded nucleophile and oxygen since have become deficient, pi bond will break towards one of the carbon, attacking at the deficient oxygen, making other carbon deficient. So the lone pair of oxygen will attack at this. So this oxygen is going to acquire partial positive charge here because it has shared its lone pair. So pi bond will break towards oxygen. Eventually you will see there will be two new bond formation taking place between carbon and oxygen, and the double bond which was between the manganese metal and oxygen will be now converted to single bond. Okay, that's how the addition is taking place. Now what is important for us to understand here, which we have been emphasizing even before we entered into mechanism, is these two oxygen which are forming two new bonds across carbon-carbon double bond have been added from the same side. Isn't it, everyone? Look at this. Both the oxygens of MnO4 have been added from the same side of carbon-carbon double bond. Hence, this step is what we are calling it as syn addition. Yes, so this is a syn addition reaction. And this is the step which is telling us that it is a syn addition. Well, once this syn addition will take place, we'll be getting a manganese ester. which can be represented like this. And now bonded to oxygen, further connected to manganese, bonded to oxygen. There is double bond O and single bond O minus. That's your manganese ester. And now this manganese ester will further undergo breaking of metal and oxygen bond, breaking of metal oxygen bond in presence of water. Well, ideally there is a precise step of mechanism. I will just virtually show it to you, but we don't really have to understand it. So just for the sake, I'm going to show it to you guys. Look, let's say this is the water molecule. All right, now water being nucleophilic, it will attack at the manganese. Pi bond will break, making this oxygen O minus. So now we will be having two O minuses. Now between any of these two O minuses, let's say that negative charge delocalizes. So this bond will break towards oxygen, making it O minus. That will accept H plus from a water. I repeat again. Okay. O attacked at manganese. This bond will break. So O will become O minus. Now both are equivalent. So further, let's say this O minus delocalizes back, or either this O minus delocalizes to regain double bond. This bond will break towards O, making it O minus. So see, manganese and oxygen bond have been broken. And now this O minus is all set to accept H plus from a solvent. So what are we getting? Formation of COH, and the remaining part over here. Now since water is attacking, this will further undergo deprotonation. Now this is how actual step takes place. And the same thing will happen one more time to break this oxygen and manganese metal bond as well. However, we don't really need this detailed steps. So what we can simply do is, look here. For the understanding, yes, we can simply show breaking of a bond like this. Between manganese metal and oxygen, and add water, HOH, and HOH. So you'll be getting formation of OH and OH, that is two OHs connected to the adjacent carbon atom, forming the vicinal diol. Plus you're going to get H2MnO4 minus, H2MnO4 minus. Okay guys, now look here. Further you will see that H2MnO4 further get processed and forms MnO2, that gives you the brown color compound. That's a different story, we don't need to know that. As of now, what we have to understand here is that the manganese, which was in a +7 oxidation state in MnO4 minus, which of course if you take an aqueous solution of that cold dilute KMnO4 which we have taken, is a pink color solution. But when that MnO4 gets added to carbon-carbon double bond to give you a diol, followed by whatever compound you're writing in whichever form, either H2MnO4 minus or MnO2. Naturally now Mn is no more in +7 oxidation state like this Mn is. Which means the pink color or the purple color which was corresponding to MnO4 minus will no more exist. Hence we call it as disappearance of pink color or decolorization of a pink color or a purple color. So whenever you take an unknown compound, let's say that unknown compound is an alkene, and if you treat that with cold dilute KMnO4, and if you see there is disappearance or decolorization of the pink color, then that will be an indication that the unknown compound which you are taken was an alkene. And this test is what we refer it as Bayer's test. Because this Bayer's test is resulting in the formation of a diol, where with respect to stereochemistry, both OHs will be on the same side. We call it as syn dihydroxylation. So guys, in simple words, the presence of double bond can be identified by treatment of that compound with KMnO4, and if you see there is a disappearance of color, that will indicate the compound was containing double bond. So at times this is also referred as test for the detection of unsaturation in an alkenes. So guys, this was one of the method of preparation of alcohol by the action of cold dilute KMnO4. Now the way you see it over here, MnO4 is used. Just like that, there is another set of reagent we use. In fact, industrially you will see that is more commonly used. But again, because it is costly, that reagent is used in a catalytic amount with one more supporting reagent. By the way, now we are talking only about that reagent. Let's not get into chemistry of that. That reagent is osmium tetroxide. So you'll always see to an alkene. Okay. OSO4. Osmium tetroxide will be used as a first condition. Once you get osmate ester, just like you got manganese ester, you'll be getting osmate ester, and that will be further treated with either sodium sulfite in water or sodium bisulfite in water. So remember, alternatively, this reagent can also be given. So in any reaction, if alkene is provided and on arrow if they mention either this or that, you're simply going to carry out syn dihydroxylation. That's going to be your product, right? Where two OHs will be on the same side. Well guys, that was about preparation of alcohol by syn dihydroxylation. Similar to this, we learned yet another reaction that is called as the anti-dihydroxylation. This anti-dihydroxylation is carried out by the action of peroxy acids on an alkene to first form an epoxide. IUPAC name we also refer them as oxyrin. Those oxyrin are further hydrolyzed in an acidic condition to give you diol. Now see, although this is two-dimensional structure, we are just trying to hint that the two OHs are on the opposite side. That is indicating it is undergoing anti-addition. So the important feature of this reaction is the earlier one was syn addition when you use cold dilute KMnO4. Now peroxy acid epoxidation followed by acid hydrolysis is going to be anti-addition. Well guys, there are lot many things to learn here for us. Let's take it one by one. First, let's talk about the peroxy acids. Well, in general, when you talk about peroxy acids, we represent it like this: R, C double bond O, single bond O, single bond OH. All right. And in this peroxy acid, this oxygen is very, very important because this is the one which will help us to carry out oxidation of carbon-carbon double bond. And of course, this can be identified by the tracing technique, where imagine if I take this oxygen as some isotopically labeled oxygen, and if I carry out reaction, in the overall reaction you will find in the product the oxygen which will be retained is going to be this isotopically labeled oxygen atom. Hence we have highlighted that. Well, so that is how you represent carboxylic acid, which is peroxy carboxylic acid. If you just take away this oxygen, this is your normal carboxylic acid. We have got one more extra oxygen which makes it peroxy acids. Now there are several examples of peroxy acids that we use, so let's get introduced to those examples. First one on your screen is peracetic acid. Well, acetic acid we all are aware is CH3 COOH COOH. We added one extra oxygen which makes it peroxyacetic acid, or you can also refer it as peracetic acid. The second one is trifluoroperacetic acid. Well, so trifluoroperacetic acid has got now withdrawing group, where all the three hydrogens we are replacing with 3 fluorine, so it can be represented as CF3. C double bond O O O H. Alright everyone. And then there is MCPBA. Well guys, many a time you will find on arrow this condition will be mentioned. MCPBA. It is an abbreviation for meta-chloroperoxybenzoic acid. I repeat, meta-chloroperoxybenzoic acid. So simply what we'll have to do now is first get the parent compound, which is benzoic acid. So structurally benzoic acid can be represented like this. C double bond O. O, and if you write H, that's going to be benzoic acid. We are adding one more O. So this is peroxy benzoic acid. At meta position, I am putting chlorine. Now this is meta-chloroperoxy benzoic acid. Now guys, other than this, there is one more reagent which we haven't mentioned here in the list, but let me tell you that is also very commonly used peroxy acid as a reagent for epoxidation, which is called as MMPP. Well, I'll write it here. MMPP. Let's understand the meaning of this and let's see what this abbreviation is for. Suppose if I have got phthalic acid. What is phthalic acid, everyone? It is benzene 1,2-dicarboxylic acid. Okay. If I write H here, it's going to be what? Phthalic acid. Similarly, if I write one more H here, if I would have taken one COH, that would have been benzoic acid. One more COH at the ortho position makes it what? Phthalic acid. Alright. Now what I'm doing, let's say from this phthalic acid part, I removed one H. So this became phthalate. Imagine that was phthalic acid. You have H here and H from here you have removed it. So now this became conjugate base of phthalic acid. So it became phthalate. Right. And out of one of the carboxylic acid, I am making peroxy. Out of two carboxylic acid, one you made peroxy. So what is this right now? This is right now monoperoxy phthalate, isn't it? Out of two COOH, I made one COOH as peroxy. But overall, it's a conjugate base because this is obtained by removal of one hydrogen atom. So phthalic acid's conjugate base is called as phthalate, isn't it? The naming of inorganic acid, what we have learned is in oxy acids, ic acid's conjugate base is called as ations. Us acid's conjugate base is called as ition. So this is phthalic acid's conjugate base, hence it was phthalate. But one of the two carboxylic acid is now in the form of monoperoxy. So monoperoxy phthalate. Now imagine if this monoperoxy phthalate ion is counterbalanced by magnesium ions. So magnesium ions are Mg+2. Whereas only one of this is in the form of phthalate ion, so charge is -1. To balance this +2, if I take it twice, so we'll be having two of this -1 charges of the phthalate ion balancing the Mg+2. Hence, this is now called as magnesium monoperoxy phthalate. Magnesium monoperoxy phthalate. Not to forget, phthalate spelling start with PTHALATE. So this is commonly called as MMPP. Magnesium monoperoxy phthalate. Magnesium monoperoxy phthalate, PTHALATE. Alright guys, so these are commonly used peroxy acids which we use for the process of epoxidation, that is forming the cyclic 3-member ring. Now let me show you the mechanism how reaction exactly takes place. Well, so let's say this is what we have got as an alkene. I'm taking in general peroxy acids, so representing it for you. Okay, guys, do you see that? RCOOOH. And when I told you, I've highlighted this oxygen which is connected to hydrogen atom. This is the one which undergoes addition, meaning carry out oxidation of carbon-carbon double bond. So now I have got, this is peroxycarboxylic acid. Now see, here, now hydrogen connected to oxygen, O being more electronegative, will pull the bonding pair of electron toward itself, making hydrogen deficient. Such deficient hydrogen will be immediately attacked by the lone pair of oxygen. So new bonding between oxygen and hydrogen will take place, which will make this oxygen atom deficient because it is sharing its electron pair. So pi bond will immediately break towards oxygen. If that happens, this carbon is going to be deficient. And in order to neutralize this deficiency, oxygen will release its electron here. As a result of releasing this electron pair or sharing this electron pair towards the carbon atom, this oxygen is going to be deficient. Hence, the sigma bond will break. Now see, as soon as this sigma bond breaks here, it develops deficiency on this oxygen atom, which generates scope of attack of pi bond of alkene towards this O. So this pi bond will break, making carbon electron rich carbon attacked at this O. Because this pi bond have been broken, this carbon is becoming partially deficient. So deficient carbon will be now attacked by electron rich oxygen. Now from where this became electron rich? Because when this H will be lost as H plus, this bond pair will entirely come on oxygen. Already it has two lone pairs, so electron rich O will attack at this carbon. So addition of this oxygen is taking place out of three, the one which is connected to H, and that too from one of the side of carbon-carbon double bond. Not to forget that these two carbons being doubly bonded, they are sp2 hybridized, so they are planar in nature. So this oxygen is getting added to this carbon-carbon double bond. Either you can show from below the plane or from above the plane. What we have shown over here is addition of oxygen from below the plane. The overall process, I'll repeat it one more time. So this is the oxygen of peroxy acid which is going to get added to carbon-carbon double bond, carrying out oxidation, resulting in the formation of epoxide or oxyrane. How does that happen? Now this lone pair of oxygen attack at H because it is delta plus. Oxygen, since sharing electron pair, becomes deficient, so pi bond breaks. Because this pi bond breaks, carbon become deficient. To neutralize this deficiency, lone pair of oxygen delocalizes. Delocalization of this lone pair make this oxygen deficient, hence it pulls the bond pair toward itself. The moment this bond breaks, this O becomes deficient and develops a scope for pi bond to attack at it. So pi bond breaks towards one of the carbon, making it rich, which attack at the deficient oxygen. Now as soon as this H is taken away by O, this bond pair will be entirely on O, making this O electron rich. And because this pi bond have been broken here, this carbon is deficient, which is attacked by this oxygen atom, which was electron rich due to loss of H plus. Such addition of oxygen is taking place from one of the side of carbon-carbon double bond. Now once this O will be added, first let us understand what is the byproduct that will be removed. Well guys, you can see now this is becoming RC double bond O. There is no bond here. So RC double bond O, this is single bond OH, meaning what is being removed is carboxylic acid. I'll write on precisely what is it. This double bond is becoming single bond which has accepted H. You see that? So carboxylic acid have been removed as a byproduct. This O got added to carbon-carbon double bond. So we can represent it this way. Alright everyone, now this is what you call it as epoxide, and hence the process will be referred as epoxidation. Okay. Now because this is three-membered cyclic ring of an ether, you can say that according to IUPAC nomenclature, these are also called as oxyrane. So in the first step, you actually prepare an oxyrane or epoxide, and then this is further subjected to acid hydrolysis. Now when you talk about acid hydrolysis, look, in an acidic conditions, since O is electron rich, it will attack at H plus and will undergo protonation. So upon protonation, now this has become OH plus. Now the moment this becomes plus and also this is 3-membered cyclic ring, we know the fact that this is strained ring. 3-membered cyclic structure is thermodynamically not stable. Hence, this kind of structure always wants to become more stable by breaking one of these two bonds, either this CO bond or this CO bond, so that the structure will become free from the angle strain. Hence, immediately, or you can say it's a fast step where water molecule attacks. Because we said peroxyacid epoxidation of alkene followed by acid hydrolysis. So under acidic condition, you're carrying out hydrolysis. Now you can see here both this carbon atom carrying delta plus charges and both being equivalent. This water is attacking from the side which is opposite to already present this oxygen molecule. Water is attacking from the opposite side of the molecule, opposite in terms of where the already existing oxygen is available. So this bond will break and followed by deprotonation. So once the proton is lost from here, effectively what is getting added is this OH group. Now guys, what we all need to understand here is attack of OH at this carbon is taking place from the opposite side of already existing OH, and hence we can call this addition as anti-addition. Alright, so in your final product everyone, we will be getting this OH. Let's say I'm showing it here. That is newly added OH from water. This bond have been broken, so this positive charge on oxygen will get neutralized. So we have got second OH and the remaining structure will look like this. So you can clearly see here we have got formation of a diol, but the two OHs which are present stereochemically, they are going to be opposite to each other. Hence we call it as anti-dihydroxylation. Another important point, when the addition is taking place, remember, out of this 3 oxygen, the O which is connected to hydrogen gets added across carbon-carbon double bond. Well guys, now based on this, suppose if we have got some question, how exactly are we going to answer those questions? Because let me tell you, the starting alkene which is given to you, imagine if you have been given precise stereochemistry of an alkene, either cis or trans. And when the addition is taking place, the product obtained, imagine if it is going to be a stereoisomers, one of the stereoisomers. So in that case, since you are starting your reaction with that reactant, which is particular stereoisomer like cis or trans, and giving you product which is a specific stereoisomer, try to recall such reaction, we refer them as stereospecific reaction. So yes, even this anti-dihydroxylation of an alkene to results in the formation of epoxide followed by diol is a stereospecific reaction. So the similar stereospecific reaction we had learnt when we studied halogenation of an alkene in presence of non-polar solvent. You remember in haloalkane, when you have got an alkene and you add Br2 in presence of CCl4, you get the corresponding product which could be either racemic mixture or it is going to be a meso compound. That reaction also we call it as stereospecific reaction. Even this is stereospecific reaction, and the trick that we applied there, we can still use it here. How? Let me show you. Look guys, now let's say if I want to find out the direct answer over here, the example what they've given is, okay, let's say we have can we say this is cis alkene? Yes, it is cis 2-butene. Right? Cis 2-butene. You can see that here. Let's say this cis 2-butene is allowed to undergo peroxyacid epoxidation and followed by acid hydroxylation. So the first condition is use of peroxy acid epoxide. So R3, not R3, RCO3H, that is peroxy acid. You may find on arrow they may mention any of the peroxy acid like trifluoroperacetic acid or MCPB or MMPP, anything. And the second condition, let's say, is acid hydrolysis. What is going to be the product? Well, guys, not to forget the trick which I had shared earlier. I'm just writing it one more time for you. Well, the trick was, if we have terms such as cis or syn, or if the two species which we have to add, if they are added from same side, for any of this term we use sign convention plus. Whereas if, let's say, starting compound is trans, if addition is anti-addition, and if two newly added group has to be added from the opposite side, we are going to use term minus. Right, everyone? Do you recall that? So the simple trick was here. Starting compound is cis, so I am using term plus. RCO3OH gives you epoxide, and then addition of water takes place from opposite side, meaning what kind of addition is that? This is an anti-addition. Since this is anti-addition, we will use term minus. Plus and minus is going to give you minus, right, everyone? So if I know my product is going to be minus, meaning what? Minus meaning the two new group which we have to add it from the opposite side. Now, which two new group are we adding? If I look at the starting compound alkene and the final product, the two new group which I see added are two OHs, right? So now you can see here 1, 2, 3, 4. So the two OHs are going to get added across this carbon-carbon double bond. So since these two carbons were equivalent, the way we have shown attack at this carbon, the attack of water could have also taken place at the other carbon as well. If water would have attacked here, then this OH would have been here, we would have shown above, and then this OH, if attack would have taken place here, this bond would have broken. So this OH we would have shown below. Meaning there are two possibilities by which you can represent the 2OH. So if I am writing the molecule in Fischer's projection, I will show it like that. Look. First carbon is methyl, second carbon carrying H, third carbon carrying H, and then fourth is also methyl. So first is methyl, last is also methyl. Well, I'm keeping this also ready. Now see, at the second and third carbon, the two OHs are going to get added. Now how are we supposed to add them? That is answered by this. Plus minus is minus. Minus meaning two new groups should be added on the opposite side of the Fischer's projection. So the two new OH which I am adding at carbon 2 and 3, I have to put them opposite side. Meaning, let's say if this is carbon 2, at carbon 2 if I am putting OH to the right of the Fischer, then at third I must put it to the left. Or second possibility is that at the second carbon I could have put OH to the left, or in that case at third it will be written to the right. Why? Because attack of water at this carbon or this carbons are equally probable, hence both ways addition is possible. So what is the remaining valency? Remaining valencies are the hydrogen atom which were there in original compound itself. So see, what product did we get? We got butane 1, 2, 3, 4, butane 2, 3 diol. Now this butane 2, 3 diol which we have obtained, if you see carefully, this carbon is a chiral carbon, even this is a chiral carbon, but there is no plane of symmetry. So no plane of symmetry meaning this is optically active isomer of butane 2, 3 diol. Similarly here at carbon number 2, that is the chiral carbon, even this is the chiral carbon. So compound containing two chiral carbon but no plane of symmetry makes it optically active. So both of this are optically active isomer of the same compound. What is that same compound? Butane 2,3-diol. So the optically active isomer of the same compound, and also if you observe them carefully, they are related to each other as a mirror images. If I put imaginary mirror here, these two are mirror images of each other, meaning they are pair of enantiomers. Because pair of enantiomers will be obtained in equal amount, because both attacks are equally probable, I would say the product obtained is a racemic mixture. So this is racemic mixture. So guys, isn't it stereospecific reaction? What are stereospecific reaction? A reaction in which particular stereoisomer results in the formation of a specific stereoisomer, meaning they are producing enantiomer. So because the product obtained is specific stereoisomer from a particular stereoisomer, we call this reaction as a stereospecific reaction. Here you can clearly see the two OH which are added are on the opposite side. Otherwise this compound would have become meso. So now think that way. Suppose if I give you another example, let's try to do it verbally. If you take trans 2-butene, carry out peroxy acid epoxidation followed by acid hydrolysis to give you diol. What is that product going to be? Let's apply the trick. So trans meaning we are going to use a trick with minus here, and anti-addition is again minus, product is going to be plus. Plus meaning the two OH which you are adding should be on the same side. So at carbon number 2 and carbon number 3, both OH, either I should show it to the right of the fissure, or both the OH I would have shown to the left of the fissure. In either of these cases, because OH would have been on the same side and having two chiral carbon, there would have been a mirror plane of symmetry. Imagine if OH is over here and H is here. If you consider an imaginary plane like this, there is going to be mirror image, which means such compound having two chiral carbon atom but possessing mirror plane of symmetry will become optically inactive. Such compound we call it as meso. So trans 2-butene upon peroxy acid epoxidation followed by hydrolysis would end up giving you meso compound. Again, particular stereoisomer would give you specific stereoisomer, that is meso. So in that case, we will call that reaction as stereospecific reactions. So guys, what did we learn from these two wonderful reactions? Alkene can be converted to diol, but the stereochemistries are exactly opposite. When you carry out syn dihydroxylation using cold dilute KMnO4 or Baeyer test, or you can say that reaction which is used for the test for the detection of unsaturation, you get diol where two OHs are on the same side. Whereas if you carry out dihydroxylation using which one? Peroxy acids epoxidation followed by acid hydrolysis, we get anti-addition where two OHs are going to be on the opposite side of each other. So guys, that was the two important reaction. You may have a question like this. Well, I want you guys to observe this. First reaction, cyclohexene is given, then KMnO4, you can certainly see here it is alkaline KMnO4 but cold and dilute, which means immediately what you should mention is that this is syn addition. Whereas MCPB, metachloroperoxybenzoic acid, well, I'll just add few things here. After this, we will also carry out acid hydrolysis, let's say. Because we don't just want to stop reaction up to formation of epoxide, we want to carry out further diol formation as well. So, because you're carrying out peroxy acid epoxidation followed by hydrolysis, we know the fact it is nothing but an anti-addition. Anti-addition. So what are going to be your products? Since it is syn addition, when you are representing this molecule in 3D, both the OHs that you are adding should be either above the plane of paper, meaning on the solid line, or going behind the plane of paper, meaning what you call it as dashed line or hatch wedge, whatever you call it. So what do you think this is going to be? Well, they are saying this is X, because I can see they have mentioned Y here. So X is going to be two OHs on the same side. Where is that? Here it is. Both the OHs represented on the solid line, meaning it is a syn addition product. Whereas anti-addition going to give you Y, where two OHs must be on the opposite side. So if one of the OH is represented on the solid line, the other one must be represented on hatch wedge, or you can say dashed line, whatever you call it. So what is that? Here it is Y. So both B and C are absolutely correct, because B is the product of syn addition and C is the Y is the product of anti-addition. So guys, the right choice is option D, both B and C. Is that clear, everyone? Excellent. Guys, proceeding further, preparation of alcohol from alkyl halide. Well, I'm sure that we have studied in detail. We have studied the entire chapter on this. That is nucleophilic substitution reactions. So, if you have got an alkyl halide treating with aqueous KOH, well, aqueous KOH indicate this is going to get dissociated as K plus and OH minus. OH minus being anionic nucleophile across carbon halogen bond, X being more electronegative. Carbon is going to acquire delta plus charge, that makes it deficient. So the deficient carbon will be attacked by the OH minus with the simultaneous loss of X. Assuming this alkyl halide as primary or secondary and nucleophile being anionic, it is going to undergo bimolecular nucleophilic substitution reaction. But of course, if your alkyl halide is tertiary, then probably only water will be required to carry out hydrolysis, but eventually you're going to get your product alcohol. So depending upon the degrees of alkyl halide, it is going to undergo either SN1 or SN2 type of reaction. But one thing is for sure, it is going to undergo nucleophilic substitution reaction. Hence we have mentioned SN, nucleophilic substitution, to give you corresponding alcohol. Just as an example, you can see here we have got an ethyl bromide. Treated with aqueous KOH, OH minus. Now this is certainly a primary alkyl halide. Aqueous KOH, strong nucleophile, less sterically hindered substrate with anionic nucleophile will certainly give you SN2. Now we can say it is definitely SN2, and the Br will be substituted by OH to give you ethanol or ethyl alcohol. So guys, this is the reaction we had studied in detail, so not spending much time on that. So alkyl halide upon hydrolysis will also give you corresponding alcohol. That is another method of preparation, but this time it is from alkyl halide. So far whatever reaction we had studied, before this we studied 5 reactions, all were from alkene, out of which first 3 reactions were giving you alcohols, that is ACH, OMDM, HBO. Next 2 reactions which we studied today were also from the alkene, but they were forming diol. And now what we are studying is from another substrate, that is alkyl halide. Now guys, just like that, we can also study preparation of alcohol from carbonyl compound. So let me tell you that we have studied the preparation of alcohol from carbonyl compounds. Well, when you talk about preparation of alcohol from carbonyl compound, there are 2 ways you can prepare alcohol from carbonyl compound. First one, which again we studied prior to this in alkyl halide, in the Grignard reagent. So when you take a Grignard reagent, treat with carbonyl compound, you get a nucleophilic addition reaction followed by hydrolysis to give you an alcohol. We have studied that. Still, I'm going to show that to you later, but not spending much time on that because we have studied that in detail. But another new reaction that we have to study today is conversion of carbonyl compounds into alcohol by a process of reduction. Well, reduction can be carried out either by catalytic hydrogenation, like you can either pass hydrogen gas in presence of nickel, platinum or palladium metal. So for the sake of understanding, if the 2 H's added across carbon-carbon double bond, it will involve breaking of one of the pi bond, because there is just one pi bond, and new bond formation between oxygen hydrogen and carbon hydrogen. That's how we will be getting RCH2 single bond OH. That is nothing but the primary alcohol. Imagine if instead of H, if I would have had an R here, it would have been a ketone. In that case, product would have been RCHR single bond OH, meaning I would have got secondary alcohol. So basically aldehydes or ketones, upon catalytic hydrogenation results in the formation of either primary or secondary alcohol. So this was pretty simple reaction. What is important is the next one. If you have either aldehydes or ketones, and if you use reducing agents such as metal hydrides, okay, if you use reducing agents such as metal hydrides, still you get formation of either primary alcohol or secondary alcohol depending upon what are your starting compound. So this is the interesting reaction that we will have to learn. Action of lithium aluminum hydride and sodium borohydride on carbonyl compounds. Guys, I'm going to show you reaction very soon. Just a short break. Alright, everyone, let's get introduced to these two reagents first. Let's say we are talking about lithium aluminum hydride and sodium borohydride. So, aluminium, we know the fact that general valency for aluminium is 3. It contains 3 hydrogen atoms connected to aluminium. Now, if you attach one more hydrogen here, then you can see aluminium individually having 4 electrons. One, 2, 3, 4. So, because in general aluminium has got only 3 electrons in its valence shell. Now we have got one extra, the charge is minus. And that is why it is aluminium hydride, where in order to neutralize this charge, in order to lose this -1 charge, it will always tend to donate one of the hydrogen in the form of H-. Hence it is hydride donor. This -1 charge is balanced by Li. So it is lithium aluminum hydride. As the name suggests, it's a hydride donor, so it will always have a tendency of donating H- ions. Because it has a tendency of donating H- ion, which can be added to any deficient carbon, in that case we say it is acting like a hydrogen donor in the form of hydride. Hence we also call it as reducing agent. So lithium aluminum hydride very commonly used as a reducing agent, and that's what we are going to do it here in case of aldehydes, ketones, acid halides, carboxylic acids, or even esters. Similar to that, if I talk about sodium borohydride. So sodium borohydride, in general valency for even boron is 3. Boron aluminum belongs to same family, so that's how it is trivalent. Let's say I'm satisfying this by hydrogen, and there is this 4th H here. So individual electron again 1, 2, 3, 4. Boron in general in a free state has got 3 valence electron. We have got 1 extra, so it is becoming anionic. That's why this is BH4 minus. And this BH4 minus is now balanced by another alkali metal, that is Na plus, which makes it sodium borohydride. Again, hydride for the same reason as it happened in case of aluminum hydride. Hydrogen connected to boron. In order to neutralize this negative charge, boron will have a tendency of losing this electron to hydrogen. So H will always come out in the form of H minus. Hence even this is considered as a hydride donor. So two reducing agent that we have got over here. The first one is lithium aluminum hydride, also commonly called as LaH. And here we have got is sodium borohydride, that is SbH. Now remember, lithium aluminum hydride is relatively a stronger reducing agent because of its ability of donating hydride at ease as compared to boron hydrogen bond. So AlH bond being weaker, it can easily lose hydride, so better reducing agent. Whereas boron hydrogen bond cannot be broken as easily as in case of aluminum hydrogen. Hence it is relatively a weak donor of hydride, so you can call it as selective reducing agent. So when it comes to carbonyl compound, you will see sodium borohydride can only reduced. Listen to me carefully everyone. Sodium borohydride can selectively be used to reduce aldehydes, ketones and acid chlorides only. Whereas lithium aluminum hydride being strong reducing agent, it reduces aldehydes, ketones, acid chlorides, which were reduced by SBH as well. Along with this, it also reduces carboxylic acids, it also reduces esters. You will see it also reduces amides, but we are not getting into amide as of now. But when you talk about carbon-carbon double bond, neither aluminum hydride or sodium borohydride can reduce the carbon-carbon double bond. So olefinic double bonds are not reduced by either of them. However, if that carbon-carbon double bond is connected to benzene ring, it's an exceptional case. Such carbon-carbon double bond is found to be getting reduced by lithium aluminum hydride but not by SBH. So I repeat, when it comes to aldehydes, ketones, acid chloride, selectively reduced by SBH, no other compound can be reduced by SBH. Now LH reduces again aldehydes, ketones, acid chloride. It also reduces carboxylic acids, also reduces ester along with amides. But when it comes to carbon-carbon double bond alone, neither SBH nor LH can reduce that. But when the double bond is connected to benzene ring, you will see LH is able to reduce. So that is exceptional case. Whatever I said, we are going to see all that. First, let us understand the general mechanism. Well, guys, you don't have to know the detailed mechanism. I will just make you understand how this takes place. Let's say if I'm talking about sodium borohydride, okay. All right, sodium borohydride. NaBH4 for our convenience, I'm writing like this. Okay, and we are allowing this to react with some carbonyl compound. Of course, this is going to be either aldehyde or ketone. So O being more electronegative, acquire delta minus, carbon acquire delta plus charge. Now one thing you'll observe, when the reaction comes with respect to sodium borohydride, it is treated with carbonyl compound in presence of water. But when it comes to lithium aluminum hydride reacts explosively in water. That's why lithium aluminum hydride will be first treated with carbonyl compound in presence of solvents such as an ether, and then you will see a hydrolysis will be carried out in the second step. But for sodium borohydride, we can directly use water. So let's say we have got sodium borohydride. So being hydride donor, through its H minus, it will attack at deficient carbon. So you can see this is nucleophilic addition. Pi bond will break and this O minus will be now connected to the remaining counter ion which you have got here, that is, let's say, Na plus. Ideally speaking, the reaction takes place where lone pair of oxygen attack at boron and then hydride is transferred to this carbon. We are not getting into mechanism here. Well, once this addition takes place, you will see out of this BH4, we had sodium borohydride, meaning we had BH3 and H. So as of now, one hydride have been added over here. So because boron still carrying 3 more hydrogen, you will need 3 more carbonyl compounds to react with this NaBH4. So one equivalent of NaBH4 reacts with 4 equivalent of carbonyl carbon. Because to one of the carbonyl carbon, one hydride will be donated. Since borohydride has got 3 more hydrogen which can be donated as H minus, you will need 3 more carbonyl compound. So whatever step we have shown over here with one carbonyl compound, it will be repeated 3 more times, okay, using 3 more equivalent of carbonyl carbon. Well, as of now, for the understanding, we are showing it with only one equivalent. So this O is going to become O minus, and you will see the hydride is attached to the carbon atom. Once this become O minus, this O minus then accept H plus from the solvent. Ideally, sodium borohydride has got hydride which attacks at the deficient carbon. This oxygen attacks at the boron being vacant orbital. And then since we have got 3 more H left, 3 more carbonyl compounds react with it. Eventually what you see, hydride is connected to carbon, oxygen became anionic. Now this anionic oxygen accept H plus from the solvent, and that's how it results in the formation of hydrogen, carbon, whatever these two valencies were, now oxygen and further hydrogen. What do we learn here, everyone, is this hydrogen that you see, this hydrogen is from metal hydride, that is NaBH4. Whereas this hydrogen is from solvent, which is, let's say, water. So we have to be very careful that when we are writing our final product, which hydrogen are we attaching to the carbonyl carbon and which atom are we attaching to the oxygen atom, because several times you will see the question will be framed in such a way that not always will be having hydrogen. You may have a deuterium or any of that kind of isotope which is available. So you have to attach appropriate isotopes of hydrogen to the carbon and oxygen atom. I repeat once again, when you have got sodium borohydride, when you treat with carbonyl compound, since this is hydride donor, hydride being nucleophilic, attacks at the deficient carbon, pi bond breaks to oxygen, which then accept H plus from the solvent. So in the product, the two H's that you see, one of the H which you see attached to the carbonyl carbon, I mean the original carbonyl carbon, is from the metal hydride donor, either from SBH or from LH. And whatever hydrogen or any other isotope connected to oxygen is always going to be from the solvent. So this is the general mechanism. So let's say, just for taking some examples over here, let's say we have been given some compounds like this. First, I'm taking with aldehydes. Let's say on arrow they have mentioned NaBH4. And now hydrolysis they are doing with, let's say, heavy water D2O. Well guys, now what we have learned, we know the fact, avoiding the detailed mechanism. Borohydride being hydride donor, it is the one which is going to attack at the deficient carbon, because this is delta plus and this was delta minus. When hydride will attack here, pi bond will break to make it anionic. Now this O minus is going to accept H plus from the solvent. So from DOD, like HOH, D plus will be accepted by oxygen. So the product obtained would be RCH. This was single bond O. Now O has attack at D, so you'll get D here, and hydride from sodium borohydride has attacked here, so this is going to be H. So this is from the metal hydride and this D is from the solvent. That is what you have to just make out the difference. Let me just take one more example for better understanding. That was example number 1. I'm taking one more example, number 2. Let's say we have got ketone this time. R C double bond O and R dash, which is treated with, let's say now we have got LiAlD4, and here now of course when you'll add LiDlA4, this is going to be in presence of ether as a solvent. See, when it comes to sodium borohydride, you will directly see it is with water or heavy water. But when it comes to lithium aluminum hydride, first you will use an ether, because LiAlH4 or LiAlD4 basically explodes in water. So to avoid that, we use ether first and then we carry out hydrolysis. So then we will be using, let's see, if I give you CD3OH. Now this could be misleading, everyone. Look, you added LiAlD4 in an ether, right, to avoid the reaction of LAH with water. So what happens, as much amount of hydrides or deuteride are required to add to carbonyl compound, those would be added. Now whatever are present in excess, we bring them in contact with external ether so that ether consumes remaining amount of D minus or H minus. Once all the H minus have been consumed, then the desired intermediate compound you get, which is like that, is further hydrolyzed. Now what is important is, here we have got D minus donor, which is going to attack at the deficient carbon. So that is our D plus. Once D minus attacks, pi bond breaks to make it O minus. Now this O minus is going to attack at the protic part. So what is protic? Although I have taken this as CD3, this is not a protic atom. Protic is the one which is attached to electronegative atom so that it can be lost in the form of H plus. Hence this is protic. So O minus will accept H plus from here, which in turn resulting in the formation of R, C, H, O. Now everyone, who attacked at carbonyl carbon? It's a deuteride. Just like hydride, it is deuteride. And who accepted, O accepted which protic atom? H from oxygen. So here I'm going to get certainly H. Okay. Well, we have taken reaction with simple aldehydes and ketones. Now let's try and understand what we explained right in the beginning of reaction. That sodium borohydride being selective reducing agent, it is going to reduce what kind of carbonyl compounds, right? So here is the table for us. Read it carefully, everyone. NaBH4 is a selective reducing agent, so selectively reduces carbonyl carbon of aldehydes, ketones and acid chloride without affecting the double bond. Whereas LiLH4 is a stronger reducing agent, it will reduce aldehydes, ketones, acid chlorides, carboxylic acid as well as ester as well as amides. We have not mentioned that. But again, lithium aluminium hydride cannot reduce the carbon-carbon double bond. So double bond is neither reduced by SBH nor by LH. But if double bond is connected to the aromatic ring, I'll take that example, then LH is found to be reducing. So let's take that as an exception for you all. Well, so functional loop aldehyde, sodium borohydride, will it reduce it? Yes, sodium borohydride can reduce it. Aluminium hydride, lithium aluminium hydride can also reduce it. I'm sure now you'll know the product. Guys, product we have seen in the previous mechanism. Ketone are reduced by SBH. It is also been reduced by LiLH4, which is stronger, of course. Acid chloride is reduced by again SBH as well as lithium aluminium hydride. But when it comes to carboxylic acid, NaBH4 being selective, it is not going to reduce carboxylic acid. LH being stronger reducing agent, it will certainly reduce carboxylic as well as ester. So ester not reduced by SBH but reduced by the LiAlH4. The only thing which I want you guys to understand, when you carry out reduction of an ester, see for rest all, the corresponding product is going to be alcohol corresponding to as many number of carbon you have. What I'm trying to tell you, whenever you'll write down a reduction product using SBH and LH, just ensure that how many carbon you have got. Like over here, I've got RCH double bond O. So the alcohol is going to be RCH2 single bond OH. Here the product is going to be RCHR single bond OH. Here chlorine will be removed. So because it's a leaving group, so you're going to get RCH2OH. Here R, again OH will be removed. So RCH2OH. See, the product that I'm writing is always keeping intact the original number of carbon atom. I'm neither subtracting nor adding any extra carbon atom. So whatever alcohol you're getting are with respect to this carbon. But in case of ester, you have got two alkyl groups. So simply remember, break this bond. So you'll get one alcohol with respect to RC double bond O and one more alcohol with respect to R dash O. So two alcohols obtained by reducing ester with lithium aluminium hydride are RCH2OH and R dash OH. Those two are going to be the product of the reduction of ester with lithium aluminium hydride. All right, everyone. Yes, now the exceptional reaction that I was talking about, double bond otherwise neither reduced by SBH nor by LH. But suppose, okay, I'll write it as exception only. Okay, now let's say if we have well guys, what is that? Can you identify the name here? This is nothing but cinnamaldehyde. Let's say this cinnamaldehyde we are treating with. Okay, so the conditions we have, number 1 is LiAl H4 in ether. Okay, and the second one followed by the hydrolysis, let's say. Now what I've told you, in general, sodium borohydride is out of question to reduce carbon-carbon double bond. If this double bond would have been isolated, meaning not in connection with benzene ring, then even LiAlH4 wouldn't be in position to reduce it. But exceptionally, when double bond is connected to the benzene ring, it can be reduced by LiAlH4. We'll take it as an exception. So the product here is benzene ring as it is. See, upon reduction, just like you do hydrogenation, put it that way. So this becomes CH2 single bond, CH2, and not to forget it is aldehyde. Aldehyde is again reduced by both of this. So aldehyde is certainly going to get reduced. This will be C. One H was already there, one more H came here, and double bond became single bond with OH. So CH2 OH. So guys, that is going to be your product, which is basically 3-phenyl propan 1-ol is your product obtained by reduction of cinnamaldehyde using lithium aluminum hydride in an ether followed by action of water. So everyone, that was all about preparation of alcohols using carbonyl compounds, but this time we learnt a new reaction, that is by reduction of carbonyl compounds either by catalytic hydrogenation or by using metal hydride reduction. Guys, we are going to see some question on this, but before that, let me show you one more reaction which we have studied already. Just a revision for you all. Okay, prior to that, one question. Well, you can see we have been given some compound where this part, everyone, this part is an ester, COO, right? And this part is ketone. Now observe the reagents. To the right hand side, they are saying you are reducing with lithium aluminum hydride. So lithium aluminum hydride reduces ketone as well as ester. So in an ester, when you get the product, what I've told you, simply have to break carbon-carbon double bond. So this part will also form an alcohol. This will also form an alcohol. So this will be CH2OH. This is also CH2OH. And this is going to be secondary alcohol because this is ketone. So the B which we are going to get will be CH2OH, CH2OH, CHOH. Can you see that? CH2OH, CH2OH and CHOH. So this B is perfect. And C, sodium borohydride selectively reduces only aldehydes, ketone and acid chloride. It will not reduce an ester group. So in C, this ester is still going to remain an ester. Only this will be reduced to secondary alcohol. So ester is still an ester and this is reduced to secondary alcohol. That is option A. Please understand, although option B is looking just like that, but this is B and C. B is the product, reduction product of lithium aluminum hydride. Here this is not B, this is B they are saying. So in B they have shown ester intact, but in B ester is not going to remain intact because LH will certainly reduce that. Alright, so your right choice is option A. Well, this is what I was talking about. We have studied in detail about this. We are just going to revise it. So Grignard reagent upon reaction with formaldehyde gives you primary alcohol. Grignard reagent with any other aldehyde gives you secondary alcohol. and the Grignard reagent with ketone gives you tertiary alcohol. Well, just to quickly revise the mechanism, we know in this Grignard reagent, the value of R is always considered as R minus. So it has predominant, you can say, ionic character. And across carbon and oxygen, carbon being less electronegative, acquire delta plus, oxygen will carry delta minus. So R minus attack at this delta plus, pi bond breaks to become O minus, which then undergoes protonation from acid hydrolysis. So the product will become RCH2 single bond OH, RCH2 single bond OH, which is primary alcohol. In case of any other aldehyde, R minus will attack at this deficient carbon, pi bond will break to make it O minus, which will accept H plus from a solvent. So what are we going to get? RCH R dash single bond OH, RCH R dash single bond OH, which is nothing but secondary alcohol, because functional loop OH is connected to secondary carbon. Down here, again we have got deficient carbon over here. So R minus will attack at the delta plus, pi bond will break to make it O minus, which will be protonated from a solvent. So what are we getting? R C R dash single bond OH, R C R dash single bond OH. The functional loop OH connected to tertiary carbon, so you'll call product as tertiary alcohol. Well guys, we have seen this. Simply to conclude, Grignard reagent upon addition to formaldehyde followed by acid hydrolysis gives you primary alcohol. Grignard reagent upon addition to any other aldehyde will give you secondary alcohol, and addition of Grignard to ketone is going to result in the formation of tertiary alcohol. Not to forget, other than this, we also studied addition reaction of a Grignard reagent to ester, acid halide, as well as dry ice, that is solid CO2, and as well as to nitrile. And we saw how those compounds can also be helpful for the preparation of alcohol. Right guys, so that was all about methods of preparation of alcohol. So just to summarize in the methods of preparation of alcohol, what all we have studied. Guys, in the class number 1, in lecture number 1, we started methods of preparation of alcohol by 3 important reactions from an alkene. That was ACH, acid catalyzed hydration of alcohol. Important features were, it involves formation of carbocation, hence rearrangement possible, and Markovnikov addition. Second one was oxymercuration, demercuration. No carbocation formation, but addition is still via Markovnikov addition. Third one was hydroboration oxidation. Hydroboration process is syn addition. In that case, there is no carbocation formation and the product was anti-Markovnikov. Those we studied in the previous lecture. Today, we continue methods of preparation again from alkene, but we saw how diol can be obtained. The first one was action of cold dilute KMnO4, that is Baeyer test. Alternatively, we can also use osmium tetroxide followed by sodium sulfite in water or sodium bisulfite in water. Both gives you syn dihydroxylation as your product. Whereas we also saw the action of peroxy acids to produce an epoxide followed by acid hydrolysis, which gives you anti-addition, and you're going to get your product which are going to be anti-diol. Based on that, how the reaction is stereospecific and how question can be solved in the easiest way, we have learned that as well. Once that was done, guys, we started learning the reduction or the preparation of alcohol from carbonyl compound. So you can reduce carbonyl compounds either by catalytic hydrogenation or using 2 important metal hydride, lithium aluminium hydride, stronger reducing agent than sodium borohydride, selective reducing agent. So sodium borohydride will reduce only aldehydes, ketones, acid chlorides, whereas lithium aluminium hydride will reduce aldehydes, ketones, acid chlorides, carboxylic acid, ester, as well as amides. None of this reagent reduces the isolated double bond, but when the double bond is connected to benzene, it is LiLH4 which can reduce it, and that is what we have seen, and this reaction we have repeated several times. Now guys, proceeding further with some questions just to revise what we have studied. Well, using all the tricks that we have done, I want you guys to use it here and try to solve it. Okay, shall we proceed, everyone? All right, so what reagent do you see? Mercuric acetate, water followed by sodium borohydride. So this is certainly not HBO. Oxymercuration, demercuration. I'll erase that. Hold on, everyone. Okay, so this is nothing but oxymercuration, demercuration. Now, when you write oxymercuration, demercuration, what are the features that you write? Okay, first one, no carbocation rearrangement. C plus is carbocation. Second feature, it still follows Markovnikov addition. Now, because there is no carbocation, I can directly write down the product by addition of water. By addition of water, as in, if water is HOH, Markovnikov meaning the negative part of the reagent will get attached to the carbon whose corresponding carbocation is more stable across double bond. So this is the secondary carbon, this is primary, relatively secondary is more stable. So OH I will attach here, H will be added over here. So I can directly say the product will be here, will be addition of OH. Right, everyone? That was OMDM. Second reaction, first, the moment you look at the conditions given, you need to identify what reaction is that. BH3THF or B2S6THF is hydroboration followed by oxidation using alkaline conditions with hydrogen peroxide. So that is HBO. An important feature of HBO, number one, first step is syn addition. Number two, no carbocation rearrangement. Number three, it gives you product with anti-Markovnikov addition. Now, since we know that it is going to give us product with anti-Markovnikov addition, looking at the carbon-carbon double bond, if I have to add water, so the negative part of the reagent must attach to that carbon whose corresponding carbocation is not stable. I mean, just for the sake of understanding, or to the carbon carrying more number of it. So OH minus will be attached over here. Right, everyone? So your product is there, it is OH, and of course H will be added to this carbon, which you, even if you don't show, that is still fine. That's a product. See guys, so once you know this important features, we are able to write down the product quickly. Aqueous KOH. Well, today we saw how alkaline hydrolysis of alkyl halide results in the formation of a product. So we have got secondary benzylic halide. Well, when we studied nucleophilic substitution, we saw how SN1 and SN2 both are favorable for allylic and benzylic halide. And aqueous KOH, so this is certainly a nucleophilic substitution reaction. OH minus will substitute this halogen atom, resulting in the formation of product, which can be represented like this. CH, CH3 and OH. And now look at this, everyone. First reaction is with LiLH4 with D2O. So not to forget, here we have got deficient carbon delta plus, and this is electron rich oxygen. So H minus from the reagent will attack at the deficient carbon. Pi bond will break towards oxygen, making it O minus, which is going to accept H plus from the D2O. So the product of first reaction will be O minus attacking at deuterium. O minus attacking at deuterium, and hydride has attacked here. Okay. Whereas in the second example, LiALD4 deuteride will attack at deficient carbon. Pi bond will break, making oxygen anionic, which will accept H plus from the solvent. So the product, well, I'll write it here. We don't have enough space, so little smaller structures I'm drawing here. Okay. So who attacked at deficient carbon? It's deuteride. So here is deuteride. And O minus got protonated with water. Normal proton OH. Okay, everyone. Alright, so those were some questions based on what we studied just now. And now finally, we are talking about some physical properties of alcohol. Well, I don't want you guys to read it at once. First, listen to me carefully. Well, we studied these properties also in case of haloalkanes and haloarenes. Here, when it comes to alcohol, when we talk about physical property, we talk about two physical property. One is the boiling point of alcohol, and second is solubility of alcohol in water. Let us first talk about boiling point of alcohol. Guys, listen to me carefully. When you talk about boiling point of alcohols, we study that with respect to 3 points. Number one, if you compare alcohol with other functional group, such as let's say ether, because ethers are isomeric with alcohol, or if you compare that with let's say alkane of a comparable molar mass, how it is going to be a trend of boiling point of this three compound. So first point, you are comparing boiling point of alcohol with other functional group of comparable molar mass. Okay, other functional group containing compounds of a comparable molar mass. Second, now we'll compare the boiling points among the alcohol itself, but of a different molar mass. Let's say we have got N-propyl alcohol, then N-butyl alcohol, N-pentyl alcohol, like that. So all of them are functional group. Now there is no change in the functional group, but the molar mass is increasing from N-propyl to N-butyl to N-pentyl. And the third thing, we will compare the boiling points of isomeric alcohols, meaning now functional group is identical, molar mass is also same, only difference will be the branching in the hydrocarbon part. For example, let's say if we have got N-butyl alcohol, then probably sec-butyl alcohol followed by third butyl alcohol, like that. Alright, so let's talk about the boiling point first. We all are aware that boiling point or any compound will have a higher boiling point or lower boiling point. That depends upon how strongly the molecules of that compounds are associated with each other. So if the force of attraction holding, rather intermolecular force of attraction holding the molecule of that particular compound is stronger, we say the boiling point of compound is relatively higher. So when you look at alcohol, in an alcohol we have got OH group. Imagine if I have got 50 molecules of alcohol, so I will be having all 50 alcohol having that OH group. So because of presence of OH group, all the molecules of alcohol will be capable of forming intermolecular hydrogen bond, right? And other than that, other than OH, there is an alkyl group as well, which is basically going to show you van der Waals force of attraction. So as many molecules of alcohols you have got, those molecules of alcohols will be associated with each other via two force of attraction. One is hydrogen bonding, intermolecular hydrogen bond. Second is van der Waals force of attraction, and to some extent there is going to be dipole-dipole attraction because of carbon-oxygen bond of an alcohol. If I compare the same thing with an ether, in case of ether there is definitely no hydrogen connected to oxygen atom, so there is no scope of hydrogen bonding. But there is oxygen and carbon bond which will have minimal dipole-dipole interaction, but maximum interaction will be via van der Waals force of attraction of the alkyl group of an ether, right? You can see here, in case of ether, there is no hydrogen. Only across carbon and oxygen there will be some polarity, so some dipole-dipole interaction, but otherwise it's going to be van der Waals force of attraction. So certainly in case of alcohol, because there is possibility of hydrogen bond, the intermolecular association of alcohol is way stronger as compared to an ether. Hence boiling point of alcohol is going to be more than ether, which are of comparable molar mass. Like ethyl alcohol and dimethyl ether have identical molar mass, but see, boiling point of the alcohol is higher than that of an ether. Similarly, if you compare them with alkane, let's say propane, again comparable molar mass, not exactly 46 but comparable. But in case of alkane, there is no polarity group because there are no atoms which differ in the electronegativities. If there is no polarity in a molecule, no scope of dipole-dipole interaction, which means molecules of propane can only be associated with each other via van der Waals force of attraction, which is weaker force of attraction as compared to hydrogen bond. Hence, intermolecular association among the alkane molecule is lesser, hence it is having least boiling point. So, in general, boiling point of alcohol is higher than that of ethers and hydrocarbons of comparable molar masses due to ability of alcohol to form intermolecular hydrogen bond. That was the first thing. Second, now compare different alcohols. So to compare different alcohols, let's say if I'm talking about probably N-propyl, N-butyl and N-pentyl alcohol. Now see, all these three are carrying OH group. So let's say you've got 50 molecules of N-propyl, 50 molecules of N-butyl and 50 molecules of N-pentyl alcohol. Because all of them are carrying OHs, all those 50 in each type are going to be associated by hydrogen bond. So hydrogen bond is not going to make difference in the boiling points of these three compounds. But the nature of hydrocarbon is changing. In N-propyl, we have got lesser number of carbon hydrogen. In N-butyl, more number of carbon. In N-pentyl, even more. As the nature of alkyl group, or you can say as the number of carbon in the alkyl group increases, van der Waals force of attraction also increases. If van der Waals force of attraction will increase, then that alcohol which is of relatively higher molar mass will be having higher boiling point. And that's why among the alcohols, boiling point increases with the increase in the number of carbon atom, meaning increase in the molar mass due to increase in the van der Waals forces. And third point which we have to compare among isomeric alcohol. Let's say I have got N-butyl alcohol, isobutyl alcohol and tert-butyl alcohol. Guys, now all of them are having 1,1 OH. Hydrogen bonding is going to be almost same. All of them are having same number of carbon atoms over here. So when you have got isomeric alcohol, then the boiling point depends upon how much surface area of that compound is available for the van der Waals force of attraction. So as you see here, from N-butyl to isobutyl to tert-butyl, what is happening to the branching in the hydrocarbon part? This is normal. There is one branch. You can say it is even more branch. As the branching increases, molecule becomes more and more compact. You can see molecules becoming more and more spherical, let's say, more compact. If it becomes more compact, its surface area to be exposed to other molecule is going to be lesser. Lesser the surface area, lesser the van der Waals force of attraction. Lesser the van der Waals force of attraction, lesser will be its boiling point. Hence, N-butyl alcohol you will see has a boiling point of 117.7 degrees Celsius, which is higher than isobutyl, which is 108 degrees Celsius. And the least is for tertiary butyl, which is 82 degrees Celsius. So as the branching increases, molecule becomes more compact, surface area decreases, boiling point also decreases. And that's what we have mentioned. Among isomeric alcohol, with the increase in branching, boiling point decreases due to decrease in the surface area because molecules are becoming more and more compact. So guys, that was all about what? Boiling points. We are going to solve some question on this. But before that, let's also talk about second property, that is solubility. Well, so solubilities of alcohols in water is due to formation of hydrogen bond with water. Well, we all are aware that if we have got an alcohol, if you put it in a water, because in case of alcohol, O is more electronegative, it has got delta plus charge and oxygen has got delta minus charge. So it has a dipole. When you put this in water, even water, we have got hydrogen connected to oxygen, which means here also we will be having delta plus on oxygen, delta plus on hydrogen, delta minus on oxygen, which means even this is a dipole. Now, when the hydrogen of an alcohol, which is itself connected to electronegative atom, comes in the closest vicinity of another electronegative atom carrying at least one lone pair, so they attract each other to form a bond called as hydrogen bonding. Similarly, the hydrogen of oxygen which carries delta plus charge, since coming in the vicinity of oxygen of alcohol carrying lone pair, even they will be associated via hydrogen bond. So in general, alcohol will be able to form 3 hydrogen bond per molecule, 2 through its lone pair and 1 through its hydrogen with another water molecule. That's how water molecule will be strongly solvated. Alcohol molecule will be strongly solvated by water molecule. More the solvation, more will be its solubility. So you will see here, alcohol molecules are found to be soluble in water because of its ability to form intermolecular hydrogen bond with waters. So solubilities of alcohol in water is due to formation of intermolecular hydrogen bonding with water. Further, the solubility increases with the decrease in the size of alkyl loop. Now imagine in this alcohol, if the value of alkyl becomes bigger and bigger, let's say methyl to ethyl to propyl to butyl to pentyl, as the number of carbon atom will increase, not to forget these alkyl groups are found to be hydrophobic. Hydrophobics are the one which are water fearing, meaning which does not have a tendency to get dissolved in water. So if hydrophobic character will increase, obviously solubility will decrease. Hence, alcohol having smaller alkyl loop, as the size of alkyl loop decreases, solubility in water increases. So guys, that was all about alcohol's solubility in water. Now based on this, let's quickly have a look at some question, guys. Well, I want you all to apply what we studied here. I'm sure you all will be able to solve all the questions here. Arrange the following compounds with the decreasing order of their boiling points. N-butane, B is 1-butanol, C is 1-pentanol. Well, now butanol and pentanol molecules can form intermolecular hydrogen bond, and that's why their boiling point is definitely more than the corresponding alkane of a comparable molar mass. Meaning, if I talk about decreasing order of boiling point, we know that A is going to be least. Okay, answer. A will have least boiling point because it cannot form intermolecular hydrogen bond. It can only be associated by weak van der Waals force of attraction. Now between B and C, both have a function loop OHS. So hydrogen bonding tendency is same in both. But as the number of carbon is increasing from butanol to pentanol, the van der Waals force of attraction will increase. More the van der Waals force of attraction, more or higher will be its boiling point. So C will have a highest boiling point as compared to B as compared to A. So this too was case number 2, where you are comparing among alcohol only with different molar mass. The first one and remaining 2 were the first case where you had a different function loops. Now let's see here. N-butyl alcohol, sec-butyl alcohol, tert-butyl alcohol. Tert-butyl alcohol. Okay guys, now the example which they have given us is such where we have got isomeric alcohol. Just to draw structures, N-butyl alcohol 1, 2, 1, 2, 3 and 4. N-butyl alcohol 1, 2, 3, 4. Sec-butyl alcohol, and here tert-butyl alcohol. Well, all of them are isomeric alcohol. Among isomeric alcohol, as the branching increases, as the branching will increase, molecule becomes more and more compact. So surface area decreases, hence boiling point also decreases. So tertiary butyl alcohol being most compact, its boiling point will be least. Sec-butyl will have relatively more boiling point, higher boiling point, and N-butyl will have the highest boiling point. So the answer here will be A, highest, then B, least is C. Alright everyone, and 2 more questions based on the decreasing order of solubilities in water. We have got methanol, ethanol, 1 propanol and 1 butanol, comparing their solubilities. See, all of them are alcohol, so all of them have alcoholic OH group. As all of them have alcoholic OH group, their ability to form hydrogen bond is due to the presence of OH. So all of them are going to form hydrogen bond. But the difference here is that the nature of hydrophobic part, that is alkyl group. This is methanol, this is ethanol, this one is propanol, and 1 butyl. 1, 2, 3, 4. See, as you're moving from methyl to ethyl to propyl to butyl in the alkyl part, the nature of hydrocarbon part is increasing. Nature of hydrocarbon part is increasing, meaning hydrophobic part. Hydrophobic part is increasing. If hydrophobic part will increase, which means the solubility decreases. Right, everyone? So, highest solubility will be for A. Your answer is going to be methanol will have highest solubility in water, then ethanol, then N-propyl alcohol, meaning 1-propanol, and then D, 1-butanol. Alright, everyone? Finally, pentane, 1, 2, 3, triol and butanol. Okay, guys, we'll draw structure here. Pentane 1, 2, 3, 4, 5. Only hydrocarbon part, there is no alcoholic OH. Pentane 1, 2, 3, triol. Okay, pentane 1, 2, 3, triol. OH, OH, OH3 carbon, and 2 more carbon I'm writing together, C2H5. And here butanol. 1, 2, 3. They have not given which butanol, I'm taking 1-butanol. Okay. 1. Clearly, N-pentane when compared with these two compounds, these two being alcoholic, they are going to show hydrogen bonding tendency. N-pentane won't show any hydrogen bonding tendency, so its solubility in water is going to be lesser, or rather least. So we know A is going to be least soluble in water. Between B and C, clearly, since in C we have got 1 OH and in B we have got 3 OH, more the number of OHs, more the scope to form intermolecular hydrogen bonding with water, hence solvation will be greater due to more number of OHs. So pentane 1, 2, 3 triol will have more hydrogen bonding tendency and solubility will be the most, hence B will be the most soluble and the least is A. C will have intermediate solubility, of course, as compared to B and A. So everyone, those were some questions based on the concept of boiling point of alcohol and solubility, which were some important physical properties which you may have in the examination, so we have covered them. So guys, that is it from our today's class of alcohols. In today's class of alcohols, we covered some important reactions: syn dihydroxylation, anti-dihydroxylation, then alkaline hydrolysis of alkyl halide via nucleophilic substitution, followed by reduction of carbonyl compound, catalytic hydrogenation, also metal hydride reduction using LH and SBase and their selectivity. Right guys, then we also saw reaction where we have seen it earlier, how addition of Grignard reagent to carbonyl compound gives you corresponding alcohols. And then, dear students, we studied physical properties of alcohol with respect to its boiling point and solubility. We solved some questions just to give you exposure of what kind of questions can be asked in the exam. Now it's your time to revise all the reactions and prepare yourself in the best possible way with us at Physics Wallah. Thank you so much guys for attending the class, and I'll see you soon in the next class with the further part, that is chemical reactions of alcohol. I'll see you soon. Thank you so much.